on what we do, and try and show some evidence that points out NASA for the liars that they are and the impossibility of what they do. And that's something that I'm about to go into right now. So, as many of you are aware, I'm an electrical engineer. I have spent the majority of my career in RF communications. I am also a ham radio operator, amateur extra class, call letters KN0DEL, which is very similar to my last name. It's called the Vanity Call. I was lucky to get it, and it's because I have the amateur extra class. And I am also a licensed broadcast engineer with radar endorsements, first class commercial license, now general class. In other words, I'm a nerd extraordinaire and have been involved in communications, computers, electronics my entire life, and it's what I like to do. So, as many of you know, I have talked many times about the idea of being able to broadcast signals, hundreds of thousands or millions or even hundreds of millions of miles. And I've talked about how ridiculous that idea is to me. And the reason that I say that is because as an RF engineer, I am fully aware of the power requirements to make those kind of journeys. So what I'm going to do today is I'm going to try and bring everybody in a little bit to my world. And I'm going to explain some basics about RF propagation, antennas, how they work, power gains and stuff like that. And I'm not going to go deeply into detail, but I am going to go far enough into detail to show you unequivocally that broadcast to the moon at a distance of 250,000 watts are barely possible. And anything beyond, a million miles is just patently ridiculous. And I'm going to say that, a lot of examples that I can use and have used before are, your typical radio stations, okay? In Colorado, we have a radio station on 850 AM, 850 kilohertz AM, called KOA. It's a talk radio station, and it is what's known as a clear channel broadcast channel. And during the day, it pretty much has a range, an effective range of pretty much everywhere around the state. Not 100% coverage by any means, because Colorado has very mountainous terrains, and that will definitely block signals when you have gigantic rock shields, essentially, to that the signal simply cannot penetrate. Now at night, that 50,000 watts remains intact, where many other radio stations have to reduce their power at night. And the reason for that is so that they don't interfere with the other radio stations around the country that are on the same frequency. Because if they're all putting out, this 50,000 watt clear channel, all you're going to hear is what's called a heterodyne noise, which is just basically squealing in the receiver. So they actually have to step that power down substantially, so that the increased conductivity of the atmosphere and the ionosphere conditions are kind of negated, so that the local channels can still broadcast in their local areas without having, massive heterodyne interference and stuff like that. So when KOA, when it becomes nighttime and the sun goes away and the ionospheric propagation characteristics change, KOA can be heard pretty much all over the country, and I would give that, given where Colorado is, that would be to say that, on good propagation, it can propagate up to 2,000 miles, okay? And this is in low broadcast frequencies. Now, microwave, you take the same power with microwave, and the path loss is just prohibitive. You can't even remotely come to that kind of broadcast distance. But I use 850 kilohertz as an example because it's one of the things that propagates best with the power applied to it. It's the most efficient in the amplifiers and stuff like that. So everybody is familiar with AM radio stations and how you can pick up certain things at night versus the day. Anybody that is familiar with CB radio and the 27 megahertz band knows that there are conditions called skip, which allow these CB signals to be heard several states away. And of course, every bandwidth or every frequency spectrum, whether it's HF, VHF, UHF, etc., microwave, all have their own propagation characteristics. But there is one thing that all of them share in common, and that includes all forms of electromagnetic radiation, which goes into all the RF frequencies, but also into UV, ultraviolet, infrared, gamma ray, X-ray, and not the least of which would be visible light. They all have to obey something that's called the inverse square law. Okay, and I've had this up here on the screen for a while, and I'm going to kind of give you an idea about what the inverse square law means. Okay, so what we talk about when we're talking about the inverse square law is if you have an electromagnetic emanation coming off of an antenna or a light bulb or whatever, as it propagates away from the source, and depending on what type of antenna array it is or whatever, omnidirectional or directional, whatever, it will expand in free space. Okay, and so when you have the electromagnetic flux lines that are coming off an antenna or whatever, they are very dense at the source. Very, very dense. And then as they propagate away, naturally, you can visualize in your mind that these flux lines would become more and more sparse and more distributed out, so that essentially at any point going away from the source antenna, you will have a diminished field strength. Okay? Now, if the antenna is an omnidirectional type and you're radiating a signal in all directions, then that same amount of radio frequency power is diminished in all directions, and it diminishes even faster, away. But for our purposes, what we're going to look at is what you're looking at here on the diagram is, say we had the source radiation, and we had, let's see, I think I brought this up here, and at 1 meter away from the transmission source, let's say you're using a light and it's spreading out over this board that's a meter away, 3 feet away, whatever. Okay, then you're going to have a certain amount of electromagnetic intensity that's going to hit this square grid that's in front of it at 1 meter. But as you propagate away from that source and you go to 2 meters away from it, well, now this same flux has got to cover an area that is literally 4 times the size. Okay, that's why they call it the inverse square law. And then as you go out to 3 meters, then you've got to cover an area that is 9 times the size. This is actually very much common sense. I don't think anybody can argue with this. It makes common sense, and it is the way that physics portrays it. In fact, I'm looking at a physics course that is actually demonstrating this. And of course, even Wikipedia, the CIA-controlled Wikipedia, would agree with this. Why? Because it is demonstrable, testable, and we know that it's for real. Okay? So the bottom line here, what I'm saying is that when you have a certain amount of intensity at the transmission source, the further you get away, not only does it get weaker because of dispersion, over a wider area, because you have a natural signal divergence, and I know Jaron knows all about this with the laser, how electromagnetic waves will diverge. I mean, that's just the way they are. The actual strength of it in power measured in watts or milliwatts or microwatts diminishes greatly, okay? Now, there are mitigating factors that can change not this law. This is a law that must be obeyed. However, there are factors that can change the actual radiated signal strength, and that can be, by the introduction of various different types of antennas or transducer media. So let's look at antennas first. When you are dealing with an RF frequency, you talk in terms of wavelength, and different frequencies have different wavelengths in free space. And what that means is that when you are dealing with the frequency in free space, what the wavelength is the time that it takes for that frequency to oscillate from baseline all the way up to a positive peak on a sine wave, if you can imagine that, back down to baseline, then going into a negative peak amplitude, and then back to baseline. So the time that it takes for that one cycle or 1 hertz of wavelength to travel through free space is called the wavelength. Okay, and the rule of thumb is that the lower the frequency, the longer the wavelength, which means that the higher the frequency goes, you will have the shorter wavelength, which is why you will see things like when you see a microwave antenna. Microwave antennas can be little bitty, teeny tiny things, not very long at all. And that's because when you're dealing with microwave frequencies, which would be like 2 gigs or 5 gigs or 10 gigs, whatever, the wavelength in free space gets much, much, much shorter. Whereas when you deal with HF, or high frequencies, the 3 to 30 megahertz band, in free space, the wavelength to go one rotation can be, 100 yards or a couple hundred yards, several hundred feet, okay? And then when you get down into the audio frequencies, say you were listening to 60 hertz, which is power frequency. Well, if you were going to irradiate that in free space, it could be several miles long or nearly a mile long, depending on where you're at. Okay, so again, all electromagnetic waves follow this rule, whether it's, whatever spectrum it is. So the higher the frequency, the shorter the wavelength. Now, one of the mitigating circumstances that can make a difference on your effective radiated power when you transmit away is a factor of gain that is introduced by the antenna. And you will see sometimes very, very large antenna arrays, like the over-the-horizon radar, and they have these enormous towers that are very, very high, and they have several arrays of them. And these antennas are meant to give you the gain to the electromagnetic radiation, more gain in free space, so that you have an effective higher, what's called effective radiated power. Okay, now there are several ways that you can go about doing this. You can make the antenna more directional, which can increase its decibel gain or effective radiated power, or you can which would be more like columnating a signal. And a good example of this to think about is if you have a night light in your house, and most night lights are like 5 watts. And you'll notice that they're just barely lit up so that, you don't blind yourself getting up to go to the bathroom at night, when you walk into the bathroom. It's just a nice dim light so that you can just see what you're doing around. Those are typically around 5 watts. But if you take that same 5 watts and you columnate it in one direction and at a very, very tight and low angle or low divergence rate into a laser, and you take that same 5 watts, it'll burn a hole in things quite easily, I might add. Okay, so that's the difference, and that's something that is akin to bringing that electromagnetic radiation into a high gain antenna. But the bottom line is, whatever happens, if you have a transmitter that's transmitting at a certain power, and you say it's transmitting at, let's say, 100 watts, and you have an antenna that gives you 3 decibels of gain. Well, the general rule of thumb is for every 3 decibels of gain, you're effectively doubling your effective radiated power. So if I take a 100-watt signal and I put it through a 3 dB gain antenna, 3 decibel gain antenna, then I'm going to have an effective radiated power of 200 watts. Okay? So one thing but this is pretty much true with anything. And again, it all goes back to the transducer. Now, when you take audio frequencies and you have like 100-watt stereo and it's kicking it and you have a great sound, and you put it into your speaker, well, you notice that most speakers are maybe 10 to 12 inches. In other words, they're just a fraction of the wavelengths that they're actually vibrating out and broadcasting. And they sound pretty loud. I mean, you put 100 watts into a speaker, you can probably hear it a couple blocks away with no problem. But if you increase the efficiency of that transducer by matching the speaker size to more the wavelength of the audio sound, in other words, if you took that speaker and you blew it up to the size of a mountain, which would be more akin to the actual wavelength of audio frequencies, and then you put 100 watts to it, you're going to hear that signal, you're going to hear that sound much, much, much further away because you have increased the gain of the transducer. And in sound, the speaker would be the transducer. In RF, the radio antenna would be considered the transducer. In lasers, the optics would be considered the transducer. So when you get into different spectrums, obviously the frequencies take on different characteristics. So a general rule of thumb then in power is anytime you double your power, you are increasing it in an expression of decibels, which is a logarithmic expression, and you are essentially increasing that power by 3 dB. Now, I'm hoping that I'm not losing anybody because I'm going to get to the meat and potatoes of this here in just a second. And the reason that I have to kind of give you this background to understand a little bit about where I'm coming from is because we're going to look at another factor, which is called free space path loss. Okay? Now, what is free space path loss? Well, in terms of a light or electromagnetic emanation, there is a certain amount of calculable and known path loss or attenuation to that signal. In other words, if we're radiating 100 watts off of an antenna and we have a path loss of so many decibels, that means that when that signal gets to an antenna or a receive point, it's going to be down significantly from what it was at the transmission point. Now, free space has a very, very, very high path loss as compared to other transmission mediums like your typical cable TV or cables or copper conductors or anything like that. Obviously, you can put a very low-level signal of just a few watts into a cable TV coaxial antenna, and you can distribute it all over a city without too much problem. Granted, there are separate amplifiers, but the idea is the same here in that when you put these type of signals through a cable or a conductor, the path loss goes way, way down because you're increasing the conductivity in the order of magnitudes. And the same goes across any type of radiation, power, whatever. It pretty much has to obey the general laws that we're talking about here. So what this physics class lecture is talking about is you have what he's showing here is your basic power of the transmission source. And then this G sub T is gain of the transmission source. And this is where we get into the gain of the antenna, whether it's really great, big, huge, or whatever. The bigger it is or the more commensurate in wavelengths that it is in resonance to on the transmission power, the more gain you're going to have or the more effective radiated power coming off of that. Okay, then you have L, which is path. That is path loss. And in free space, like I just said, path loss is extremely high. And the higher the frequency, by the way, in path loss, the more the severe the path loss will be. In other words, if I was to take a 2.4 gigahertz wireless signal, okay, and I had 10 watts of power coming off that 2.4 wireless signal, it's going to go a whole lot less distance than if I were to use, again, going back to that radio station frequency of 850 kilohertz at 10 watts is going to go much, much, much further because the path loss is less at those lower frequencies. Now, this is significant. Why is it significant? Because one of the factors that NASA uses, of course, is they don't use HF or LF or low frequency or anything like that in their communications with their spacecraft. They are using microwave frequencies, which can be anything from, I believe, 1 gigahertz on up. And I believe typically their frequencies are in the 10 gigahertz range, anywhere in there. Okay.
Hey, Bob, make sure you're sharing your screen.
I am sharing my screen.
It isn't showing.
Okay, I don't think it's showing on the feed.
Oh my goodness. Oh my goodness. Okay, I'm glad you said that. I am so sorry, everybody. I don't know. It says you're screen sharing and presenting to everyone. All right, let me stop and restart. I don't know what happened there. Very odd. All right, thanks for telling me that. So let's go screen share. Screen one. Share.
Okay, I don't know.
Present to everyone. Let's see if that brings it up. All right, come on. Gonna come up. Gonna come up. Talk to me, Goose. There it is. Oh, there it is. Okay. Sorry, guys. All right. So let me go back and at least show you these things. I know everybody saw this because I saw this earlier. And this is the inverse square law that I was talking about. All right, when I was talking about the radiation pattern, when you get 1 meter away, you have so much distribution of, let's call it light, just so you can visualize it easier. 1 meter away, it pretty much covers this entire square. But when you get 2 meters away, because of the light divergence or signal divergence, RF light, whatever, electromagnetic radiation, you get 2 meters away, and suddenly now, because of the inverse square law, 2 meters now necessitates that it will become 4 times less potent or strong at 2 meters away. And then when you get 3 times away, the square of 3 is 9. And so now you have the same source that has to cover a source, a receive area of 9 times, okay, that size. All right, so that's the inverse square law. And I think, pretty much that I was talking about here, we have your power transmit, gain transmitter, and here's your little parabolic dish, and you've all seen on the ISS the little thing that spins around, or you can use these little parabolic dishes to point at a certain target, and the most common things that people can refer to those are like the DirecTV or Dish Network dishes, okay? Great. So he's demonstrating here that you've got your power transmitter, then you've got your gain of the transmitter, which, as I just talked about, gets you a higher effective radiated power. Then from there, you have your path loss, which is extremely high in free space. Then you have kind of the reverse process, the gain of the receiving antenna, and the same rule of thumb goes for the receiving antenna. The larger the antenna you have with respect to the wavelength that you are using, the more gain you're going to be able to pull in. In other words, the more sensitive you're going to be able to receive these signals at. And then you've got power at the receiver. And of course, receivers typically have a threshold of what the minimum amount of signal or power input that can be differentiated from what's called background noise, or just white noise or something like that. It's basically called the noise floor. All right. So if your signal is coming in below your noise floor, then it doesn't matter how good your receiver is, because the noise floor, or the noise at the floor, has a higher amplitude than the intelligent signal that it's trying to differentiate from. Okay. So that's it pretty much in a nutshell. Now, so what I'm going to show you now is we have these nifty little things these days in the 21st century that do all these calculations for you. When I was working in microwave, we had to do these things manually. And as I said, it's a very, long and crazy logarithmic formula, because it is a logarithmic formula. Okay. But now we have these handy-dandy conversions tools, which are great, because this makes it much easier to show you this without driving you crazy with the math. So what we're going to do, let me explain to you a little bit what we're looking at here, okay? So we're going to look at free space loss calculators, okay? And basically what it does is it lets us put in distances in miles, kilometers, meters, centimeters, yards, feet, inches, whatever. We're going to use miles because this is America, and anybody can go to this Pasternak site and do it in kilometers for the European people, but it works the same way regardless, okay? Next factor we have is the frequency that we're going to be using. You can enter it in gigahertz or megahertz. And we're going to show you a little bit of demonstration of both, showing you that as the frequency goes higher, the path loss substantially increases, okay? Then you have this transmitter gain and dB, all right? And essentially what this is talking about is going back to this diagram, coming off the antenna is your effective radiated power. And that's taking into consideration the power coming from the final amplifier of the transmitter, going through, whatever losses. There's cable loss, but we're not going to talk about that. And then finally getting to the antenna, which gives it another additional gain factor, which then gives you what is called an effective radiated power, okay? So when we use this transmitter gain, it doesn't really matter what the power is initially, but the transmitter gain will give you an effective radiated power on the output, and that's all we're really worried about, because we're dealing these equations in decibels. Now, when you calculate free space loss and stuff like that, you don't do it in terms of watts, and I think this is done largely to just add another factor in to confuse people, and so they never think about it. Because honestly, as an RF engineer, I look at this now and I'm like, how in the hell did I miss this? Well, I missed it because of my indoctrinated thinking, just like I missed the impossibility of 60 to 100 mile microwave shots because of an alleged curvature of the Earth. We were making them, but the curvature of the Earth absolutely prohibits that from happening. Something I never thought about, something I guarantee you that no other RF engineer has thought about, or if they have, then they're probably not going to be going to their boss and telling them, hey, we got a problem here, this shouldn't be working, because they'd probably be fired. I'm sure you all understand how that works. All right, so the next thing we're going to do is, because we're not dealing in watts, which we're so used to using in our transmit power, we're going to be converting watts into decibels, okay? Now, you have two basic figures that are used in decibels. You have dBm, which means decibels with reference to 1 milliwatt, which is 1/1000th of a watt. And then you just have simple just dB, okay, which dB watts, which would be the watts, okay. So basically, if we have 1 dB, there's basically a 30 decibel difference, okay, between dBm and dBW. So if we say 30, goes back to 0. 30 dBm is 0 dBW, okay. And this is gonna get really clear here in just a minute. So what I'm going to do, first of all, is we're going to take this free space loss calculator, and we're going to find out how much power we have to be able to transmit over certain distances, okay? And again, this is all handy dandy, it's wonderful, all calculated for us. And as you can tell here, I have already done a calculation of 250,000 miles, and I'm sure anybody that thinks about that would be equal to a one-way trip to the moon, all right? So let's turn this down, and let's do what the amateurs are doing, the ham radio amateurs, and let's put in 146 megahertz, okay? And let's say that the transmitter gain, is going to be a plus 60. Well, let's actually put this in here. Enter watts. Now, hams cannot put any more than 2,000 watts. They are limited to 2,000 watts. Okay, and they may be able to get a gain figure of 6 to 9 dB. So again, going back to our rule of thumb, if we have 2,000 watts maximum power input, which gives us maybe 1,500 watts at best output, and we give that through 9 dB, so we're tripling that power. So we go 1,500 watts to 3,000 watts is 3 dB, 3,000 watts to 6,000 watts is 6 dB, and 6,000 watts to 12,000 watts is 9 dB. So we have 12,000 watts ERP, all right?
Bob, this just in. If people at home are completely lost, you're not alone.
Okay. Yes, and I'm sorry. I will definitely get through this. But again, I have to give you this background. All right. So basically, what this saying is this: this is a 70 dB maximum power output, even with the best of circumstances. So let's go back to this. Transmitter gain, 70 dB. All right. Receiver gain, let's give it, I don't know, let's give it that same 9 dB. Calculate it. Free space path loss is 108 decibels. Okay. So what does that mean? That means to overcome this 108 dB loss of power, now we have to go to dBW, and let's put in 108, convert it. That means that we have to have a transmit power, and you can see this is a big number, 448,734. So we're talking about 63 billion, 95,734,448 watts.
Jeez.
Just to overcome the path loss. All right? Do you see a problem here? And this is only going one way to the moon. All right? Now let's look at something really ridiculous. Okay? Let's look at a distance, and let's all of a sudden now let's go to NASA's frequencies, and let's go to 10 gigahertz. All right? And let's say that they're transmitting, I don't know. And then we know the satellites can't put out a whole lot of power because they only have solar arrays on them. So let's say those solar arrays maybe are capable of delivering, let's say, 10,000 watts, which is absurd. But let's give them the benefit.
Tell us that number, Bob? Is that something that's reported?
That's something that's actually classified. I do have some of those figures, but we can just apply a little bit of common sense here to this. All right. So transmitter gain, again, let's give them the benefit of the doubt and say that they can run 10 kW. That's going to be 70 dB. All right. So 70 dB. And now let's go to, I don't know, let's go to the sun. All right. The sun, and the reason the sun is not an unreasonable example because Jupiter is a lot further away, right? Stuff like that. So let's just do a shot for the sun. 93 million miles, 10 gigahertz. There's our power. Let's give them the advantage of having a high gain receiver antenna, and let's give them let's give them 20 dB of gain there. All right, calculate. Now we're talking about a free space path loss of 185.9 decibels. Well, let's go back to our decibel converter. So let's go 185 dB, which means that to make the trip to the sun, now we have to have, oh my, this is such a big number, I don't even know what it is, but it's in the petawatts, okay? You're getting the idea here, guys. In other words, there is no freaking way on God's green earth that we can be making transmissions of these distances given the idea of how much power is on board these satellites. All right? I think, and of course there are other factors. Yes, there are other losses, there are other gains, whatever. But this is a very, trimmed down version to simply show you, even if I'm off by a factor of 1 million or even 1 billion, it's impossible. It is impossible to make these journeys at these distances, okay? This is the point that I've been talking about all these times. I have just used all mainstream sources, all mainstream information, everything, and I have shown, even in a physics lecture, how all of this works. The impossibility of transmitting a signal, it can't even be done to the moon. All right, especially with what the hams can do. So, what are the ham radio operators talking about when they say, "Well, we're doing these EME bounces"? Well, first of all, EME bounce, if you're talking about a 250,000 mile trip, that means that you've got a 500,000 mile or half a mile or half a million mile journey, that this limited power that the hams can use to go up there and bounce back. As I've just shown, this is patently impossible. So what is it that they're bouncing these signals off of? Well, I'm going to tell you, about 100 miles up, there's something that reflects RF radio waves. You can call it the ionosphere, you can call it the firmament, whatever you want to call it, that is what it is that is reflecting these signals back. All right? So, James Neal says, I'm not factoring gravity. That's my problem. Okay, that's my problem. That's funny. All right, anyway. So what the hams are actually bouncing off of is either the ionosphere, assuming that even actually exists, or some sort of firmament or glass-like structure that is described in the Bible that's reflecting these signals back. So yes, they honestly do believe that they're doing it, but as I have just shown, using all mainstream calculations and all mainstream science, the impossibility of it goes beyond silly, right? I mean, there's just no way that we can make these types of broadcasts. And common sense tells you that here on good old plain Earth, because if we have 50,000 watts and a relatively high gain antenna for AM radio station KOA, and we can barely cover the state, all right, now we're starting to put things in perspective. All right, this is what I have been trying to tell people. And again, there are several other factors, but believe me, nothing that's going to make a million or a billion times difference in these calculations. So I'm hoping that I didn't lose everybody. You know, go back and look at this, do some research on these, do the calculations yourself, look up antenna gain factors, and also how far down in the mud or signals can be retrieved from ground noise level. And typically, typical receiver sensitivity is minus 100 dBm, okay? So that's typical, some a little more, some a little less, depending on the frequency. Again, all these are factors, but the bottom line is that no matter what frequency they're using, and they would be far better off using low frequencies than they would be microwave, but even they won't make the distance, even though they have considerably less path loss. So the other thing that I want you to consider is that because all forms of electromagnetic radiation have to follow this inverse square law, and also will have path losses that increase exponentially the higher you go in frequency. Now I want you to start thinking about light from stars that is emanating from allegedly thousands of light years away. And you start to see how ridiculous this entire idea is, okay? So I hope that people are getting this. I'm sorry if I lost you. Yes, I'm going to hand it over to Jaron because everybody's saying, give me a timeout. But again, people, you have to understand how this shoots a hole right through NASA's head in every way, shape, and form. So take it away, Jaron.
Yeah, no, I'm actually trying to follow along now by looking up, like, what do they say Curiosity is using? Because, yeah, I mean, what you described, I'm so shocked that it shouldn't shock me, but I mean, this should have already been called out, that it's impossible for them to even communicate. When you put up that wattage, Bob, are you talking about constant power, or are you talking about, like, blasts of that?
I'm talking about constant power, and it has to be constant power because remember, they're sending back data streams. Right, so you can't be doing it in bursts, right?
Yeah. I'm trying to see if there's any of these numbers that we could plug back in just to see what they say. But there's obviously a ton of numbers on this page.
Well, and whatever they are, like I said, you can never go beyond the power generation capability of the solar arrays on the spacecraft. And anybody that has solar panels on their house knows that in order to power a medium-sized house, I don't know, 2,000, maybe 2,500 square feet, you need several panels. And I don't know what the individual panels are, you know, that for solar power is, but you need several of those on your roof, okay? And then you're still only dealing with being able to power the house up to maybe 15 kilowatts or 15,000 watts, which is pretty typical, I think, for an average house, anywhere 50 to 20,000 watts, depending on, how many electronic gizmos you have in your house and stuff like that. So this is kind of putting it in perspective. Think about solar arrays and people in the house. If people could generate megawatts, then you'd never have to pay. You could sell power back to the power companies, and of course, some people actually do that. But the typical solar arrangement that you see on people's houses, which consists of maybe 6, 7, 8, or 9 arrays, panels, are generating maybe 1,500 watts per panel, I would guess, and that's probably best.
Let me just read you what this page says, and you tell me what you think about this. It says, when rovers communicate directly with Earth from Mars, they send messages via both low-gain antenna and high-gain antenna, both being capable of receiving the 7.2 gigahertz uplink signal and transmitting the 8.4 gigahertz downlink signal. The LGA is a choked circular wave guide design having about 70 degrees beam width pattern and about 8, I think it's decibel, 6 dBIC, I don't know what that is, boresight gain at 7.2 and 8.4 gigahertz. Although showing some directivity that will satisfy any amateur radio, according NASA engineers, the LGA is considered as a quasi-omnidirectional antenna. It is right that the X-band we are used to work with beams 10 times narrower. It doesn't even sound like an English sentence.
Well, what that means essentially is omnidirectional means that it beams in all directions at one time, which means that you're going to have a much higher loss in the inverse square law because it's not focusing in one direction, it's an omni. Now, when they're talking about beaming it in a certain width, okay, that means that they're essentially doing what they're doing like with a laser. They're columnating it, or they're trying to put the majority of that RF signal into one direction so that you have less loss due to the inverse square law. But less loss simply because you're taking all the energy that would be radiated in the wrong direction and you're redirecting it and making it a more potent signal in the direction that you desire, or towards Earth in this case.
And it says about all of the communications will go through the HGA, a dish 28 centimeters in diameter that beams data directly to DSN over the X-band, 8 to 12 gigahertz. The downlink data rate to the orbiter is established with the HGA at 264 bytes per second, 1.85 kilobits per second, while the uplink data rate is 125 bits per second, utilizing the LGA. Isn't that extremely low?
Yeah.
Yeah.
That's exactly right. And of course, they convolute it with all these technical terms that most people have no idea what it means. And that's, of course, part of their formula. But, and that's why I've tried to break it down into basic common sense, that people can relate to as far as, radio stations or your CB radio, which does 5 watts. And anybody that's been on CB has used like an omnidirectional, or if they have a beam on their house, then they can increase that length, by a factor of 2 to 3.
Wouldn't temperature affect that?
Well, that's one of those variables that I didn't include. But yes, I'm absolutely.
I mean, because Mars is going to be, at least as far as I know, 0 degrees or less. Isn't it that cold there?
Yeah. Oh, well, okay. I see what you're saying. As far as how it affects the electromagnetic radiation, not sure. The only thing that I would say that in terms of light, when you have a lower temperature in an atmosphere, it reduces what's called the density altitude of the atmosphere. So if you have a 70-degree day and you're at 5,000 feet, then you're going to have a specific density altitude. But if you reduce your temperature down to 0 degrees, that air is going to be considerably denser. And so it's going to be emulating an altitude, and I'm echoing really bad, guys, I know this. That's okay. It's going to be emulating an altitude that is considerably lower than this. And this is something that pilots are very, very familiar with and trained in, and it's called density altitude. In other words, if you're doing a flight calculation and you need to, lift a certain amount of weight, and every airplane comes with its specifications, you may be able to load it up, to that maximum weight. But if it's a hot day, then you're starting to play with fire because you don't have as much dense air to be able to produce lift for that airplane. So temperature is a factor in stuff like that. It's also a factor in visible things because the denser the air is,